5.12, this is our last lesson in calculus. So, implicit relationships still follow the same rules as functions. If dy dx equals 0 or dy dx does not exist at a point, then that point is a critical point. If the second derivative is greater than 0 at a point, then the graph is concave up at that point. So, consider the curve, this function here, at the point -1, 1/2. Is the curve increasing or decreasing? Is the curve increasing or decreasing? What they're looking for is what is dy dx? Is it positive or negative when x is -1 and y is 1/2? So what you want to do right here is implicitly differentiate this function so we can get a dy dx out of it. So derivative of 3x cubed is 9x squared. Derivative of 3 is just 0. Now, in order to find the derivative of ln of parentheses 4y squared, you have to use the chain rule. So it's 1 over 4y squared multiplied by the derivative of 4y squared, which is 8y dy dx. And then you can multiply the 4y squared over 9x squared times 4y squared and divide the 8y over here equals dy dx. And then if you just plug in -1 and 1/2, so we could simplify this, simplify the 4a into a 1/2, the y squared over y into just a y on top, but we can just plug in these values here directly. Plug in x for -1, plug in 1/2 for y. So 9 parentheses -1 squared times 4 parentheses 1/2 squared over 8 parentheses 1/2. That's equal to dy dx. And then if we do that all by hand or on the calculator, you should get a value of 9 over 4 or 2.25 if you got a decimal. So to answer this question, the curve is increasing because dy dx, and I'll just put the point here, negative dy dx at -1 comma 1/2 is greater than 0. And that is your answer for question 1. So, second question here. Consider the curve at the point -2 comma 0. Is the curve concave up or concave down? Concave up or concave down? They're looking for the sign of the second derivative. So we have to find well, I guess we have to implicitly differentiate this twice to get a second derivative. So let's do the first derivative first though. 2x equals e to the y dy dx. If you divide both sides by e to the y, you have 2x over e to the y is equal to dy dx. That's our first derivative. Now to find the second derivative, we have to use the quotient rule. Low d high, so e to the y times 2 minus high d low, 2x times the derivative of ey, which is e to the y dy dx, all over low, e to the y squared. So now we plug in -2 for x and 0 for y. So we just do e to the 0 times 2 minus, well, you have to enter the fraction on the calculator, but it's e to the 0 times 2 minus 2 times -2 times e to the 0 dy dx. But if you remember, dy dx, we can't plug anything for here, but dy dx is 2x over e to the y. So we could do 2 times -2 over e to the 0 all over e to the 0 squared. And if you do all this on the calculator, you end up getting a value of equals -14. So the second derivative is equal to negative 14. And again, just a reminder, this dy dx is 2x over e to the y. We just rewrote it so we can plug in the negative 2 for x, 0 for y. So to answer this question, concave down because the second derivative at negative 2 comma 0 is less than 0. That is your answer for question 2. Again, everything here, we are not doing anything new. These should all look familiar to what we've done so far. Final question here, consider the curve y cubed minus y equals x squared. It's known that the first derivative is 2x over 3y squared minus 1, and the second derivative is this whole thing right here. They did some work for you there already. At the point 0, comma 1, is the curve relative max, relative min, or neither, and justify. So this is utilizing what we learned from 5.7. The first derivative, when the first derivative is equal to 0, we know we have a critical point. And let's say if the second derivative is less than 0, negative, so you have a critical point and it's a concave down function, that would give you a relative maximum. Vice versa, I'll do this all the way here on the left. If you have f prime equal to 0, but your second derivative is greater than 0, you have a critical point, but the function is concave up. You can also have the critical points when f prime does not exist, but you'll more commonly see 0. So what we can do here now is just find what's the value of the first derivative. dy dx at 0, comma 1, that's equal to 2 times 0 over 3 times parenthesis 1 squared minus 1, and well, that gives you a 0. So that's a critical point. Now let's see what the second derivative is. This one's easy here because they already gave us the first and second derivative. We just have to plug in numbers. The second derivative at 0, comma 1 is 2 times 3 parentheses 1 squared minus 1 minus 24 0 squared 1 over 3 times 1 squared minus 1 squared, and that's just equal to 2 over 2, which is 1. Well, the second fraction here all goes to 0, and it's a 2 over 2 for the first fraction, which is a 1. So we can see, to answer this question, we have a relative min at 0, comma 1 because dy dx is equal to 0 and the second derivative is greater than 0. So that's like this first, it's like the one we had on the left here. Sorry. This is like what we had on the left right here. When the first derivative is 0 and the second derivative is positive, we have our critical point and a U-shaped curve, so that gives us a relative min. So this is our answer for this last problem here. You can go ahead and start the practice.